So earlier we talked about we need to provide the K to K-means and its affiliated algorithms. And now, so how can we decide this K? There's three methods that that are typically in use. The first one is the empirical method. It gives you, you can use this formula. N is the number of observations. You can try number of clusters to be this number using number of observations to compute. Empirical methods, right? It's just in practice, we try this, it works most of the times, but how do we know it's the best? We don't. Elbow method is based on the observation that when we increase the goodness of the clustering is measured by the sum of squared error. If we do total within sum of squared error, so within every cluster, total sum of within cluster squared error, we will get a number of error count, error score. When we increase the number of clusters, this error total within sum of square would decrease. The intuition here is because when clusters are smaller, they're tighter. The data in those small clusters are more similar to each other. Therefore, their sum of squares should be lower, and the total would be also lower. However, when we oversplit those good clusters, this effect will reduce, because when we have good clusters being divided, we have one additional error number to add to the total number. So in reality, when we plot this out using the number of clusters and the total within sum of square, we will find a curve like this. And a lot of times we will find this curve have similar slope, but there is a sudden change at a certain point. And this sudden change is called the elbow. And we will take this number of clusters at this elbow point as the ideal number of clusters that we want. So we were dividing, and we still improve the performance to a greater extent until we hit the optimal number of clusters, and further split those clusters, our reduction of errors reduces. So this is the logic between the elbow method. In practice, this the elbow point is not always clear. So here, even in this diagram, I could see 2 is elbow. And you will tell me 4 is elbow. Somebody will say 8 is elbow. When you have a situation like this, you could actually do cross-validation for a set of candidate K values, do M cross-validation, and then compute the sum of squared errors and pick the best K. This method is rarely used. I have not read people using this method, actually. Another method that gives you more clear solution is to use the Chalouette coefficient. Again, the idea is to measure the quality of the clusters and plot this quality. This quality is going to be, instead of the sum of squared errors, we're going to use Chalouette coefficient. And again, what you see here is we try out a different number of clusters, and then for every cluster, we measure its quality. So K, we have run 10 times, we run the algorithm 10 times. Every time we produce a different number of clusters. clusters. And for each every clusterings, we find the Shadow-Watt score called Shadow-Watt width. Then how do we compute this score? We can probably start by saying that this score is computed for each every observation. Then the average of this score over all observations is the Shadow-Watt width, the average Shadow-Watt width that's going to be plotted here. The greater the number, the better the clusters. Shadow-Watt coefficient, SO, is defined as this. So we need to know B and A. What's AO? AO is the intra-cluster distance. It's the average distance between O and other data points in the same cluster. So it measures the tightness of a cluster. So this formula says that let's compute for each every data point in this cluster with A, we compute the distance and then we do the average. BO is a function that measures the separateness of the clusters. So it's the minimum average distance from O to all other clusters. Okay. So we can look at this formula. It says take the minimum among a set of these values. What this value is? The value is the average distance of O to all the other points that's not in its own cluster. So this C, J, J is not equals I, and this O is belongs to the cluster I. So this is a CI's observation in CI. So we take we find the minimum of those distance. So O to all other points in other clusters, find the minimum. So this measures the separateness of the clusters. The greater the value, the better the clusters are separated. And then we combine this A and O and formulate this Shadow-Watt coefficient, also called Shadow-Watt width, for one data point. Shadow-Watt coefficient is ranged from -1 to +1. So what we see here is the greater this value is, then the greater B is, smaller A is. So that's the ideal best clusters that we want to get. So when we plot it out, it always clearly show you where your best clustering is. Again, this Shadow-Watt method can give you a clear indication what numbers that you should choose to find the best number of clusters. But you can see the computation still assumes the shape of the clusters being globular or rounded, ball-shaped clusters. So do we have questions on Shadow-Watt coefficient? R provides all those computation methods for you. So
yeah, I have a question.
Yeah.
Is this graph from the same data set like the elbow method graph is?
Is this graph from what?
The same data set like the slides before? Like
oh,
the
no,
elbow?
no.
Oh, okay.
They're not, yeah. Should I make a note about this on the slides? Okay, on a different data set, yes. No, it's
maybe
not
because,
the same.
I was just thinking the one says 2, the other maybe 4, so.
Yeah. Most of time you probably will see that they agree to a certain extent. One may be saying 4, the other may be saying 5. In general, they should be consistent. It's just it's harder to tell here. Here you have multiple choices.
Yeah. Okay.
The other that's it's clear.
Is silhouette method preferred to elbow method, or we just use both?
It's my preferred method. I found it's easier to argue. When I have a elbow like this, I don't feel confident to argue that the 4 is the right cluster.
Does elbow also have the globular constraint or assumption?
Right. Some of the squared arrows, if you use this arrow, it does. Because later on we're going to see some of the so those earlier we see those clusters with very different shapes. The large long line S-shaped clusters, they can give you look at our sum of square arrow definition. It assumes this centroid.
Is that because some of the squared of the errors is essentially like a linear distance?
When you have a center point assumed, your sum of squared will be optimized when you have a global shape.
That pi r square, right, versus pi r, so it's globular.
Mm-hmm.
Oops, sorry.